Hello, welcome to the New York City Category Theory Seminar. It's October 11th, and today we're going to have Thiago Alexandre talk about internal homotopy theories. Take it away.
Okay, thank you very much. I am Thiago. I was born in São Paulo, Brazil. I did both my bachelor's and my master's degree there in mathematics at the University of São Paulo. And now I am in the second year of my PhD in mathematics at the University of São Paulo. My advisors are Professor Mariano from São Paulo and Professor Georges Montignotis from Paris.
And they work in these derivators also?
Yeah, Georges Montignotis is basically the propagator of the theory of derivators around the world. He was the one who typed the most part of the manuscript.
Grothendieck's manuscript.
Yeah, the original Grothendieck's manuscript. So, and he also introduced the theory of test categories and Grothendieck homotopy theories, and so. Mariano is more like a categorical logician. So, but I am working with both. And so today I would like to talk about internal homotopy theories.
So I'm just lowering the lights.
Yeah. Oh. So my talk will be divided in two parts. In the first part, I will present the theory of derivators, and focusing on the original Grothendieck's and Haller's motivations. And at the second part, I'm going to talk about internal homotopy theories, which is a work in progress that I'm still developing, and I'm happy to share with you, and I would appreciate any comments you might have. So, okay. So first, historical overview of the theory of derivators. So, the idea of derivators appeared for the first time in mathematics with Grothendieck and pursuing stacks. However, the first published axiomatization appeared only 5 years later with Alex Haller, independently, and in his seminal paper, Homotopy Theories. The most important work in the theory of derivators is the Grothendieck manuscript, which is Les Dérivateurs. It's a very long manuscript with 1800 pages. And then further developments came with Keller and Frank in the theory of derivators and the relationship between derivators and triangulated categories. So this is, but why derivators? So the main goal with the theory of derivators is to provide a good framework for both homological and homotopical algebra at once. And following the Euclidean principle that homotopical algebra is non-additive homological algebra. I say this because Euclid himself claims in the introduction of his very beautiful lecture, Homotopical Algebra, where he introduced the concept of model categories, that what he was trying to do is to work with some kind of non-additive or non-abelian homological algebra, and that's what would be homotopical algebra.
I thought you said non-linear.
Yeah, it's non-linear. I think that he means non-linear, yeah, but non-additive in some sense, because linear categories, I think that the linear categories that he had in mind were the median categories, and he tries to reproduce some constructions in homological algebra in a non-additive context. So a fundamental notion. So starting from homological algebra, so just a comment here before. What I mean with this is that derivator algebra is a kind of generalization of both homotopical algebra and homological algebra at once. So it unifies both the subjects in a single formalism. So, and that's something. So beginning with homological algebra. So a fundamental notion in homological algebra, which was introduced by Grothendieck and Grothendieck, is the construction of the derived category for an abelian category. So if we start from an abelian category A, if if you want, you can think that A is the category of abelian groups or sheaves of abelian groups over topological space. We first enlarged this abelian category to a complex abelian category. So, and then we obtained a derived category by formal inverting all the quasi-isomorphisms. So, quasi-isomorphism is a morphism between the complexes inducing an isomorphism on the cohomology groups. So the idea is that in the derived category, complexes which have the same cohomology groups are effectively the same complexes. So in this construction became a foundation in homological algebra after Grothendieck and Verdier. But people started to realize that it was not sufficient for the whole picture of homological algebra. So the first problem already appeared because those derived categories are not abelian in general. Yet they have a really special structure, which is the structure of a triangulated category. So what is it? Basically a triangle.
So it's every triangulated category is a derived category? Or the other way around?
No, it's not the case.
Okay.
We have triangulated categories which
are not derived and
do not derive from an abelian category necessarily. There is an important appearing an important triangulated category in algebraic topology, which is the triangulated category of spectra, which is constructed from CW complexes and topological information, geometric information. They not come from necessarily from an abelian category this way. But a triangulated category is a triple formed by an additive category, T, an additive autoequivalence, sigma, which is called usually the suspension, and a class of distinguished triangles, which are diagrams of this form here, such that some axioms are satisfied. I'm not going into the axioms now, but what we may have in mind, which are the most important properties of triangulated categories, are that the discounts appearing here at these distinguished triangles, they are not unique up to a unique isomorphism. They are unique up to isomorphism, but not to a single canonical isomorphism. So they do not satisfy a universal property in some sense. Yet they play a fundamental role in the theory of triangulated categories because an arrow F is an isomorphism in a triangulated category precisely when the discounts are zero, are the zero object of the category. And another important property is that the evident inclusion of an abelian category into the derived category takes exact sequences into distinguished triangles. So these are very important. This properties captures the essence of a triangulated category coming from a derived category.
Okay, fine. But every abelian category is a triangulated category?
No, they are different, very different in nature.
But every abelian category has such a, for every morphism there's a whatever, you know?
Yeah, with every abelian category we can, first we take for each object of A, we can take the complex concentrated in degree 0 of this object, and then we project on the derived category via localization this complex, which is basically the same object, but with the arrows of the derived categories are different, but the objects are the complexes of the objects of the abelian category.
So you have three different notions: abelian categories, derived categories of abelian categories, and then triangulated categories.
Yeah, but the notion of triangulated categories appeared when Verdier realized the structure of this derived categories. So the kind of natural structure they came with.
So again, every derived category has a triangulated structure.
Yeah, every derived category.
But there are triangulated categories that don't come from derived categories.
Yeah, that's.
Okay, so now we separate it then. Okay, fine.
So we have this evident inclusion, which takes exact sequences, but it does not preserves any abelian structure from A. As I said, very few triangulated categories are abelian, almost trivial cases, and so it's not really. They are not the really interesting cases. So no, but we can make some criticism of derived categories. So the first one is that these derived categories, they are not even finitely complete and co-complete in general. And it's a problem because the cones appear in distinguished triangles. They are deduced from the cone construction in the category of complexes, and which is in fact a columnate construction. It's a push-out construction. So, however, these cones are not columnates in the derived category. They are, the first example, they are columnates only up to homotopy of complexes. That's what it would be.
So that's typical in a homotopy category. A homotopy category doesn't have limits and colimits.
Yeah, this is...
So it's the same problem.
The same problem, yes.
But they do have homotopy limits and homotopy colimits.
Yes, that's what I'm going to...
So it's the same, okay, fine.
Yeah, this is very common. So they have just this homotopical limit notion. And we could try to say, oh, let's just work directly with homotopical limits into the derived category instead of working with ordinary limits and colimits. But there is a problem yet, because diagrams taken directly in the derived category, they do not have enough information to determine, and not even to define properly the homotopy limits and homotopical limits, in the sense that they satisfy some universal property. So, and it's a problem also because it is expected that this inclusion of the abelian category into its derived category is a universal additive factor from an abelian category to a triangulated category sending exact sequences into distinguished triangles. But precisely because of the problem of non-universality of the cone that I mentioned above, the derived category is not satisfying this universal property. And but everything happens as it were the case. So there is something lacking in the theory of triangulated categories alone for homological algebra. And now, as we were already talking, the same problems with homotopy limits and homotopical limits appear in homological algebra are also present in homotopical algebra. So, in homotopical algebra, we are interested in the study of localizations of localizers. So, for now, I'm going to use a lot this term, so it's good that we have in mind what it means. So, by localizers, I mean couples formed by a category N and a certain class W of arrows in this category that we would like to think as being genuine isomorphisms. They are usually called weak equivalents or weak homotopy equivalences. And the localization of a localizer of this kind is another category denoted that way. I denote this way at least. And equipped with a functor, which I call the localizing functor, that inverts all the W equivalents, all the arrows, and all the arrows sending all the arrows from W to isomorphisms. And this is universal with respect to this condition. So any other functor from N to a second category N, let's say, inverting all the W equivalents, factors through gamma by a unit functor. So this localization satisfies, it's characterized by this universal property.
So in particular, derived category is a localized category where you invert all the quasi-isomorphisms.
Yeah, precisely. When we take M as being the category of complexes, and we take W as being the class of quasi-isomorphisms, then the localization is the derived category. So, in some sense, this is why the problem in homotopical algebra generalizes what is happening in homological algebra. But the same problems are also present, as I said. So these categories But first point that these categories, the localization of a localizer, they are better understood when the couple, the localizer, carries an extra structure. As it has a equivalent model category structure in the sense of equivalent, or fibrant or cofibrant structure in the sense of Brown, which generalizes the notion of equivalent model category structure. But in general, whenever we can do this, these localizations are far from being complete again. They are almost never, or even finitely complete or co-complete. But in several situations, we have some kind of construction of a homotop limit or a homotopical limit for diagrams. And again, taking diagrams taken directly into this localization do not have enough information to determine or define these homotopical limits and co-limits. So in order to understand how to think about these homotop limits and co-limits, there is another problem here, which is the following thing, that then what is happening actually, the point is that localizers are not homotopically intrinsic in the sense that a localizer is a kind of presentation or modelization of its homotopic category. So the homotopic category is just the localization. But in general, there is a branch of localizers very different from the original localizer you have in nature, with the same homotopic category, with equivalent homotopic category. So, for instance, the homotopic category of homotop types of CW complexes, which is a classical homotopic category in mathematics, it can be presented by modelized using topological space, simplicial sets, small categories, perceived over non-empty finite sets, which are symmetric simplicial sets. Actually, after the theory of the theory of test categories of Grothendieck, we know that there are a lot of per-sheaf types modelizations of the category of homotop types. So the classical category of homotop types anyway. So when we work with a particular presentation, a particular localizer, we're working with a presentation. It's like if we were working with a vector space, but studying this vector space only looking at the basis of this vector spaces and not with in an intrinsic way. It's like we are doing geometry with coordinates, but we are just studying the coordinates. And when we think about the diagrams are taken into the category M, so they're not intrinsically justified in this way. The homotop limits and homotopical limits, whatever they are, they must be intrinsic. So this is the problem. So we must have a way to do homotop theory intrinsically. And this is one of the things that the theory of derivators or pre-derivators do. But here, before
I just want to say, I mean, giving a presentation of a group is that intrinsic in your language, right? Because you can have generators and relations in one and generators and relation in another, and they're somehow the groups are the same.
Yeah.
Right, but it's still legitimate.
Yeah, but the problem is that it can be that sometimes we are proving, I don't know, things or properties about this group using
the presentation.
The presentation, and we have to take care if it does not depend of the presentation of the group. And so sometimes it does not, but we have to be careful about this possibility. And this is a possibility that happens in homotop theory with localizers. So it's like the same thing when we're doing topos theory and we want to understand intrinsic properties of the topos, but we kind of privilegiate a particular site of the function.
Right.
So we have to take care that we are not proving just properties of the site. And
right. So, but in topos theory, is there a non-intrinsic way of doing things?
In topos theory, yes.
How?
We can. This is something I'm going to discuss
Oh, okay,
in the part of internal.
Sorry, okay, sorry.
Homotopy theories, but before I introduce the idea of Grothendieck and Haller, I'm just going to remember quickly what are limits and colimits. So if we have a category, just remembering that if I is a small category, then we have this category of diagrams, which is just functors from I to C, and we have always a constant diagram functor from C to the category of diagrams. So taking each object to the constant diagram, fixing this object. And the category C admits limits, or respectively colimits of type I, precisely when the above functor admits a right, or respectively a left adjoint. And is the right adjoint of this functor, or respectively the left adjoint, which is the limit, or respectively the colimit functor. So given a diagram, okay, so we can of course redefine our notation, but a category C is complete, or respectively co-complete, when it admits limits or colimits of diagrams of any type. And I'm just remember this to see how we define limits and colimits in functorial terms. So, now there is another notion which is very close to limits and colimits, which are the can extensions. So for every functor between small categories, there is of course a canonical functor, which is this inverse image, which is defined by composition this way, with this formula that I wrote. And a category C admits right, with respect to the left can extensions, when for every functor, the inverse image functor, U star, admits a right, or respectively a left adjoint. Usually denoted this way, so the right and the left adjoint. And if the category admits right or left adjoints, we can see that this category is complete or co-complete, because we can define, take this functor here, which is for each category I, which is the unit functor, the canonical functor from I to the point category, right? We can just define the limit and the colimit as respectively as the right can extension and the left can extension of this functor. But the reciprocal is also true. So if we have a category which is complete, or respectively co-complete, it has all limits and colimits for diagrams of any type, then it admits right and can extensions. We can recover the right and left can extensions from just in terms of the limits and colimits. So the idea of derivators is to generalize this in order to understand homotopy limits and homotopical limits. So that's the idea of Grothendieck and Haller. It's a very simple idea at the end, but they just observed that localizers never appear alone. So they are always accompanied by diagram categories, and each one of these diagram categories came also with a class of termwise weak equivalences defined this way, right? So actually, when we have a localizer, precisely as when we have a category, we have already all the categories of diagrams of this category. For a localizer, you also have all the localizers of diagrams, so which are these localizers here. And so we can form derived categories in some sense, which are, or homotopy categories, which are defined as being those localizations here. And moreover, it is an easy consequence of the universality. Localizations that any functor between small categories induces a canonical inverse image.
I'm sorry, what's FL?
Oh, it's the set of arrows.
Set of?
The set of arrows of the category.
Yeah,
I'm sorry, I didn't know that.
Okay. So 1 second. These diagram categories came with classes term-wide weak equivalences. Wi. Oh, so W are morphisms in M.
Yeah.
And Wi are morphisms in M.
Term-wise.
Point-wise. Okay, so.
Point-wise.
So every component of the natural transformation is in W.
Yeah, precisely.
Right. So we can form the derived categories, B of I. Okay.
Yeah, so we have for every localizer of this way, we have not only his homotop category alone, but we have a branch of homotopy categories for each small category I. And in some sense, and also as, using the universal property of localization, we can verify that any factor between small categories induces a canonical inverse image between the derived categories, which is, of course, goes in the opposite direction. But in some sense, we should think about this. Just
could you back up for a second? You want to get rid of localizers because it's not intrinsic, but you still have it. You still have M and W.
Yeah.
Hasn't finished yet.
Oh, okay. Okay, all right. Sorry.
But at the end, we are going to
get rid of them.
So here's like a motivation to see what is happening when we have a localizer.
Okay, good.
And we can just forget about the localizer at the end and stay just with D. So, because in some sense, these categories are the true categories of diagrams from the homotopical point of view, which are the homotopical diagrams. So, and we can recover, of course, the homotopic category, evaluating this construction D at the point category. And for every small category I, of course, that the canonical functor induces an inverse image this way. And now we can use this to define properly what are homotop limits and homotopical limits. So we can say, generalize what's happening in the case of limits and colimits, just saying that the homotop limit, when it exists, is a right adjoint of this functor, and a homotopical limit is a left adjoint of this functor. So, but now you're dealing only with the homotop categories directly, the homotop category itself, and the homotop categories of diagrams. So, and that's it. But when we do this, we're dealing with a generalization of Ken extensions, which Heller called homotopical Ken extensions. And I guess that Grothendieck called direct cohomological images.
So wait, I'm sorry. So if I had started with a model category and I did this process, taking literal Kahn extensions wouldn't give you the correct notion of homotopy limits, right?
No, if you just take the diagrams directly into the homotopy category, no, it does not.
But here you're taking like object-wise weak equivalences, localizing at that. But even the thing you're saying here wouldn't give you the normal notion of homotopy limit.
Oh no, this gives the right notion.
Oh, it does?
Yeah, that's the definition. This gives that's the correct notion in the concrete cases. When we're doing, for instance, when the localizer came from the model category, that's what the...
Really? So if I took a model category, I localize it, I'm in the homotopy category, you're saying that if I have a diagram, well, typically the homotopy limit is in the model category, though.
Actually, yeah, in some sense, but not because we are localizing. So when we localize here, so it's like when we when we do this localization, we are dealing with diagrams up to like homotopy equivalence. So there is more information. That's the point. There is more information in this category than in the category of diagrams alone. That's the what was. I don't know if it was.
Yeah, I'm just kind of surprised by that. Yeah, keep going.
Can I borrow a piece of chalk for a second?
Oh, of course.
Something it's about this. It's rather than looking at ho of C to the diagram, you look at ho of C and that.
Sure.
So,
Yeah, but I mean,
Yeah.
it's surprising that that even works.
right, so this would give you limits and co-limits in the diagram, in the homotopy category, and this would give you homotopy limits and co-limits.
Yeah, but that's not how they're defined for model categories.
Right.
You mean like when we take the exponential C, I, it is not a model category in general. That's the...
Well, if the model category is nice enough.
Yeah,
There's
yeah,
two
right.
model structures associated to them.
Yeah.
If C has a model structure, then C to the I has two models,
Yeah.
plural model structures.
Yeah, that's but that in fact that's something I'm going to comment about this.
Yeah, I'm sorry. I
But,
just
sorry,
think
no,
it's-
thank you.
Sorry, go,
But
sorry, you go. You're doing good. You're doing
Yeah,
good.
but no, but it was a good question actually then. But where I was just okay. So now I'm finally going to define derivators. What are derivators? I was just talking about why derivators, but so the formal definition. First, we define what is a pre-derivator. Pre-derivator, it's a two factor from the category of small categories into the two categories of categories. But here I'm going to present it in a concrete way. So for each small category, a derivator D assigns a category D of A, the derived category in some sense. So and for each functor between small categories, it assigns a functor which is the inverse image of n. And for each natural transformation between functors between small categories, a natural transformation, which is also the inverse image of alpha here, also in the opposite direction. And of course that the two functoriality conditions must be satisfied, which I wrote here. So of course it must preserve, it must be compatible with the composition, take units to units, identity to identities. It must be also compatible with the horizontal compositions of natural transformations and take, of course, mixture functorial. And also, I forgot the star here. There should be a star here. Sorry, but the horizontal composition also, we also must have, it must also be compatible with the horizontal composition.
Is this Heller's definition also? I think Heller it makes it contravariant on the functors, not on the natural transformation.
Yeah, that's not the Heller's definition. That's something I would remark that some authors, actually a great part of them, they define a pre-derivator just being one contravariant, but two covariant, like Heller do this.
Mm-hmm.
But Grothendieck does this way. Here I'm following the Grothendieck's notations. He defines a pre-derivator as being contravariant both in one arrows and two arrows. But there is not a great difference between the two approaches are equal at the end. They have the same. They are the same. You prove the same things. You just have to reverse some arrows sometimes. But the difference is that in this way, we are privilegiating a cohomological point of view. And when we take the inverse image of the two arrows in a covariant way, then we are privilegiating homological point of view. That's the difference, but this is not a problem. But sometimes actually it's easier to work with two arrows in a covariant way. So for instance, the difference is that, as I'm going to show in the examples here, so here's some examples of pre-derivators. The first one, that for every category C, there's assignment, so taking a small category A to, I denote this way, C of A, the category of presheaves over A with values in C. So A up here is the dual category of A. So if we choose to work with the homological orientation, then we don't take the dual category of A here. We take just vectors from A to C, not from the dual category of A to C. But and we define a different, but these notions are dual. So here we can define for every category C this pre-derivator, which is pre-derivators of this kind are the representable derivators in some sense. So, and as I mentioned before, also for every localizer, we can define a pre-derivator by taking the category of presheaves and localizing the class of arrows, which are term-wise weak equivalences. It happens that I'm presenting this way because it happens that in geometry, when in geometrical situations, it's more common to think in cohomological terms because of cohomology of topos, but this is not a problem. And the third example, which is also important, so these are basically the major examples of pre-derivators, is that if D is a pre-derivator, then I is a small category, then this assignment here is also a pre-derivator. So it's very simple but very important formal construction, the theory of pre-derivators. So now I'm going to skip this because I'm afraid I will not have time to talk about internal homotopy theories, but this is not a. Here I'm just saying it's just a characterization of when a pre-derivator is representable, but it's also one of the axioms of derivators. But now, what is important is that pre-derivators, there is a notion of morphism between pre-derivators, which is, and there is also a notion of morphisms between morphisms of pre-derivators, a kind of modification. So we can arrange pre-derivators in a two category, and I'm going to proceed a little bit faster in these slides, but the point is that there is an evident two functor from the categories of categories into the two categories of pre-derivators, assigning each category to the pre-derivators of presheaves defined by this category C. And this is an embedding of the two category of categories into the two categories of pre-derivators, such that the essential images are precisely the representable pre-derivators, or what we could call presheave theories in some sense. So in this way, pre-derivators is an extension of the theory of categories. So the theory of pre-derivators is an extension of the theory of categories. We are enlarging, and because pre-derivators are just, in some sense, they are just presheaves over categories. Just.
That's like saying topological spaces, toposes are generalizations of topological spaces.
Yeah, it goes in this direction. So, or even if we have a category, we have all the presheaves of this category over this category. So we are not only looking at the representable presheaves. So in this sense, pre-derivators are like, the categories are just the representable pre-derivators, so we have more objects here.
But one gets the impression that representable pre-derivators are not the interesting ones.
Yeah, they're not, because we don't need, if we work only with representable
We don't have any notion of homotopy.
Yeah, we could stay just with categories and we don't need a theory of pre-derivators. But the point is that these pre-derivators defined by localizers are not almost never representable already. Of course, if W is the class of isomorphisms in C, then this is just equivalent to the pre-derivator defined by C.
Right.
But in general, they are not representable. So, and another important thing is that whenever we have a morphism of localizers, so what is a morphism of localizers? A morphism of localizers is a filter between the underlying categories, preserving weak equivalences. So, every morphism of localizers can be canonically extended to a morphism of pre-derivators. There is a lot of two-categorical yoga in doing this, but it's not hard, it's just we have to work a little bit. But there is this canonically extension, which is induced via the universal property of localizations. That's a point interesting here. We could say, oh, a pre-derivator is localizable when it's equivalent to the pre-derivator associated, so some localizer. I propose actually to think that a homotopy theory is a localizable pre-derivator. That's not the Haller's definitions. For Haller, homotopy theory is a derivator, but in some sense, Haller was only dealing with complete homotopy theories. And the point of this definition has to do with some developments in the theory of infinite categories. And now it's broadly accepted that an infinite one category or a quasi-category is a homotopy theory or presents a homotopy theory. And we have some results showing that homotopy quasi-categories, infinite categories are equivalent to localizers, to the two category of localizers, in order to be the homotopy theory of homotopy theories, some sense. So this is why I propose this definition as a good definition of homotopy theory. I don't know if this is correct or not.
Sorry, can you say that one more time so that you can define some two-category, just the objects are quasi-categories, and you're saying that's equivalent to the two-category of localizable pre-derivators?
It's equivalent, in the sense that we have the model structure of the Joyo model structure of the category of quasi-categories, of infinite one categories. And we have also, we can induce a Dewar-Kahn model structure in the category of localizers.
Okay, good.
And these are equivalent.
Great, thank you.
Yeah. So it's in a sense that because we think that the category of quasi-categories is like the category of homotopy theories. So the homotopy theory of quasi-categories, the homotopy theories of homotopy theories. But this is, and these are equivalent to the homotopy theories of localizers. So,
there's a paper by Rezik called the Homotopy theory, Homotopy of homotopy theories, or something like that. Is that the same thing?
Yeah, I think that in this paper he discussed about the homotopy theory of homotopy theories, and if the paper I'm thinking about.
Right, but it's before quasi-category, it's before, but it's.
Yes, it's before. It just I think that the subject of this paper is that the homotopy category of homotopy categories cannot be concrete. I guess that's the point. But quasi-categories were accepted as being the. I don't know if I'm totally in agreement with this, to be honest. I'm not the greatest fan of infinite one categories.
Neither was Heller. He didn't like it. And if you look at his paper, he says we're going to just use the bare minimum two categories that we need. But you didn't,
This is but I propose this definition just to if some people from infinite categories can what up theory is an infinite category? No, okay, then it's a localizable pre-derivator. But I will stay with derivators and prefer them. So they're not mainstream nowadays. But the point here is that a pre-derivator.
just one second. You have a notion of a pre-derivator. You're also going to have the notion of a derivator.
Yeah.
Okay. And how is it related to a homotopy theory?
Yes, basically the idea is that a derivator, that's I'm going to talk about now,
okay.
But the point is that, the point is that if we follow the idea that the true category of pre-derivators is an extension of the true category of categories, then we could say that derivators are to pre-derivators as complete and co-complete categories are to categories. So they are the completed concomplete version of pre-derivators. So they are the pre-derivators admitting homotop limits and homotopical limits. So essentially, essentially a derivator is a pre-derivator such that for every functor between small categories, the inverse image functor admits both a right and a left adjoint, usually denoted this way. Now, of course, that we can define a notion of left derivator and a notion of right derivator. So a left derivator when these inverse image functors are left adjoints, and it's a right derivator when these inverse image functors are right adjoints. Again, there is a choice of terminology here, because some authors define a left derivator as being a pre-derivator for which the inverse image functors admit a left adjoint. So there is a lot of confusion here. But since I choose to work with the cohomological orientation, that's the terminology I must use. Now, of course, there are some other axioms of derivators, but the other axioms are just axioms prescribing how to compute this this homotopical kind of extensions. The essential idea is that for a derivator, it admits homotopical kind of extensions.
Did Grothendieck know that they were Kahn extensions, and he just called them something else? Or, I mean, he came after Kahn. He must have known.
Yeah, I think that Grothendieck called them, sometimes he called them homotopical kind of extensions. So
yeah, he did use that notation, that names.
Yeah, he used the name as well. But in the manuscript, Les Dérivateurs, he used most the term direct cohomological or direct homological images. I don't know why. Maybe it was because he was thinking because he uses a lot of homological algebra in order to inspire him to find results in the theory of derivators. I guess that's why he used this terminology. But I sometimes I use both terminology. So that's what a derivator is in some sense. As I said, the other axioms are related to the computation of this homotopical Ken extensions here. So sometimes a left derivator is to pre-derivators as complete categories, R2 categories, and a right derivator is to pre-derivators as co-complete categories, R2 categories. And the derivator is when you have both. You have homotopical right and left homotopical and extensions. So it's the case of a B-complete category, but B-complete derivator. So, and of course, when we have this, since we have this homotopical can extensions, we can define the homotop limits and homotopical limits the way I mentioned before. So considering the unit functor from the category to the point category. So in this way, those homotop limits and homotopical limits are defined intrinsically to D, because and even when just like coming back here, even when the pre-derivator is localizable, because when I say pre-derivator is localizable, I'm just saying that, oh, we have some localizer presenting this pre-derivator, but it does not mean that we have a unique localizer. So it just is the same thing with topos, so Grothendieck topos. So when we think, oh, a topos is a category of sheaves over some site, some small site. But we can have a lot of sites, small sites, presenting the same topos. And here we can have a lot of localizers presenting the same homotop theory, which is the pre-derivator. And we could even think about things as Morita equivalence between localizers, which are localizers presenting the same derivator or equivalent derivators, or pre-derivators. But in practice, how one constructs derivators? They are hard to construct. Pre-derivators are sometimes easier, but the derivators are hard because we have to prove the existence of the homotopical extensions, and this is not easy to do. So, but a great part of derivators in practice are constructed from model categories, or at least from good localizers. And another branch of derivators are the ones deduced from other derivators. So, for instance, a Grothendieck localizer is a localizer such that the pre-derivator it defines is a derivator. So, a Grothendieck localizer is, in some sense, a localizer presenting some complete and incomplete homotop theory. Now, a Quillen localizer is a localizer for which we have two notions of errors, fibrations and cofibrations, such that this quadruple here is a Quillen model category structure. Quillen model structure. Now, there is a result proved by Cieszynski that showing that every Quillen localizer is a Grothendieck localizer. This is very tricky because as we already were talking before, discussing, when we take, it's not true that when we take diagrams over a model category, we have a model category. So, this is not true in general. For this to happen, we have the model category must have some kind of functorial factorizations, fibrations and cofibrations. So, but it is true for combinatorial model categories. So combinatorial model categories are model categories for which the underlying category is a presentable category, and we have the cofibrations and the weak cofibrations are generated with some. They are accessible. They are generated with a small set of cofibrations and weak cofibrations in a good way. So, but for combinatorial model categories, which are the case of the most cases that we have in practice, they are all combinatorial model categories in practice almost. We can see that they are exponentiable in the sense that if you take diagrams over n, and we take the class of term-wise equivalences, then we can define a model category with taking term-wise fibrations, or taking, we have both, have the injective and the projective model categories. But Trzynski proved this theorem for a general equivalent localizer. He didn't assume in his paper, which unfortunately I forgot to put here as a reference, but he didn't have to assume this condition of combination.
I mean, equivalent has fibrations and cofibrations, and because of that, you can deal with homotopy limits and homotopy co-limits, no?
Yeah, in some sense, the idea of fibrations and cofibrations is that, yes, in some sense, because we can use them to construct the homotopical extensions, which are the total derived functors, but also because of the fundamental theorem of homotopical algebra, which is a kind of abstraction of what happens in the case of topological spaces, that we can take the category of topological spaces, and it has a model category where the weak equivalences are the weak homotopicals in the sense that they are continuous maps inducing isomorphism on the homotopical groups. But you can also take just not all topological spaces, you can take just the CW complexes and define thus the homotopy equivalence in the usual sense, the strong homotopic equivalence. And it happens that the White-Hand theorem claims that these localizations are equivalent. But it's much more easier to work with CW complexes as just homotopy equivalences than weak homotopy equivalence, because we don't have to compute the homotopy groups, which are very hard. Actually, we don't know how to compute that. And this is what something very important, that when we have fibrations and cofibrations, we can concretely describe the homotopic category, the localization of M with respect to W, as a category where using the cofibrant-fibrant replacement, and use a notion of homotopy, which appears naturally from the axioms. It's the same notion of we have cylinders and all the homotopical intuition from algebraic topology. So, but here we don't. In general, as I was saying, the theorem proved by Trzynski is tricky because we have to define a very special model category, which is a reading model category. It's a very technical. And first, we have to prove that it defines a derivator only for central diagrams, and then we generalize to but it is true that every equivalent localizer, not only combinatorial model categories, define Grothendieck localizer. So in this sense, the homotopical algebra of derivators generalizes the equivalent homotopical algebra. Okay, but in practice, as I'm saying, in order to define derivators, we have to find model categories. So this is not so. So derivators are good to work theoretically in intrinsic, but they are not good to when you have a concrete example because you will have to deal with model categories at the end. There is no way. But to make theory, abstract theory, it's better to work with derivators. And this is another important example. And this also shows because why it's important to develop the theory of derivators. Because sometimes we can define derivators from other derivators. So sometimes working with the formalism of derivators, we can achieve results like this, that for every derivator D and every small category I, this pre-derivator Di that I defined here, so
cross I.
Yeah, this one is also a derivator. So this this construction preserves the property of being a derivator.
Just let's talk about the future here. How many slides do you have? And we would like to see some of the internal homotopy, you know, the logic stuff.
I think that I still have.
Holy cow!
I'm sorry, I don't know why.
Okay.
But how much time do we have?
So let's go for another 15, 20 minutes.
Okay.
So. Good Lord. Okay. Okay. So you make the decision you want. So let's. It's 10 after 8. Let's go to 8:30.
Okay. 10. I think I'm going just try to explain.
No, it's very enjoyable. You're making sense out of it. It's very nice.
Oh, but I'll see what I can do.
Okay, you do it.
So. Now, I'm going to the subject of internal theories properly. So, okay, so why internal homotopy theories? Because that's the point. I would like to study internal homotopy theories. I would like to internalize homotopy theories in a topos. So that's something that we already have some cases, like the case of the homotopy theory of simplicial sets, but I would like to understand this problem in general. So I would like to understand how to internalize a general localizer into a topos in order to do internal homotopy theory. But here things start to become a little bit hard, because the point was the first part, how we internalize a category in a topos. So we could take sheaves over a topos with values in this category. But it happens that sheaves over a topos with values in an arbitrary category, they add with 2 points of view, an external and an internal one. So in order to understand this, suppose, for instance, that this category N here is the category of set theoretic models of some theory, T, let's say, some that I call some synthetic code. It can be a first order theory, it can be a sketch, which is a kind of diagrammatic syntax, it can be some kind of type theory. I don't know, but what is important is that this kind of synthetic code can be, is able to be interpreted in every topos.
So you mean like a sheaf of groups versus a group internal to sheaves?
Yeah, precisely. But this is one of the examples. Yeah, this is one of the examples, because we have the theory of groups, and we can internalize the notion of groups inside every topos. But for an arbitrary category, it may be that we don't have this synthetic code, so this is more complicated. And in some sense, when we have the external point of view, we are privilegiating the category of set theoretic models. We're like we take this as an intended model, and we take sheaves over with values in this category. But from an internal point of view, we don't have a privilegiated model. We have the syntax, and the syntax is more like a matrix of models, which gives you the category of models to a topos and return. So that's a difference between perspectives, really. And why this problem is so complicated in general? Because, you know, when some category of structured sets defined only in terms of finite limits, these are the essentially algebraic categories, like monoids, groups, abelian groups, categories, simplicial sets, and so on. Then it is true that the external point of view is equivalent to the internal point of view. So, for instance, sheaves over a topos with values in the category of groups is equivalent to group objects internal to the topos. And the same is true for categories, monoids, and so on. Like simplicial objects in the topos, it's equivalent to sheaves over the, simplicial objects in the topos, which is the internal version, is equivalent to the category of sheaves over the topos with values in the category of simplicial sets. However, the external and the internal point of view, sheaves, they do not agree in general. So we have here two crucial examples. The first example is the example of local ring, which is plays a central role in algebraic geometry. Is that, for instance, you can talk about local rings internal to a topos. So, for instance, if X is a topos with not many points, then the local rings internal to this topos could be described as internal rings, such that each one of the fibers is a local ring for each point of the topos. So, just recalling a point of the topos is a geometric morphism from the point topos, which is the category of sets, to the topos X. But in this case, the category of sheaves over the topos with values in the category of local rings is not equivalent to the category of internal local rings. And here is another example which is much more sensible for homotopy theory. That if we consider category K of Ken complexes as a model for the theory of infinite groupoids, whatever it is, so we know that the category of Ken complexes indeed modelize the theory of infinite groupoids. Because we proved the homotopy hypothesis for this. But then we can also internalize K in every topos X, producing this category that I denoted this way, let's say of internal infinite groupoids. Yet this is it's not true, again, that sheaves over a topos with values in the category of Ken complex is equivalent to the internal infinite groupoids. And you know, I guess this is one of the reasons that Grothendieck didn't like very much to the idea of modelizing infinite groupoids with Ken complexes. He proposed the idea of infinite groupoids, of course, in Grothendieck's text, and he was aware that the Ken complexes modelized infinite groupoids, but this is a problem of Ken complexes, actually. We can the way we internalize is not so good. We internalize Ken complexes using some notion of local right-linked property. So that's why Grothendieck proposed the notion of infinite groupoid, which is close to our intuition that an infinite groupoid is we have objects, arrows in between arrows, between arrows, and so on, and all 10 are invariable. And Martin-Yotis gave a precise definition of this structure. It's a structure of infinite complexity, but this is still defined only in terms of finite limits. So for this structure, the notion of external and internal sheaves agree, but for this structure, the homotopy hypothesis is not proved yet. So it's an open conjecture.
What does local rings need that it's not essentially algebraic?
Local rings, the axioms defining the axiom which define local ring is the one which says every element, or it's invariable, this element is invariable, or 1 minus this element is invariable. Or another way to say is define a local ring is that it is a ring with only one maximal ideal. It has only one maximal ideal. So actually this is the local rings, it's a geometric theory. The theory of local rings is a geometric theory, but not an algebraic theory in the sense that
You said you need essentially algebraic.
Essentially algebraic. It's not essentially algebraic. It's geometric, really geometric. So this is
because you have the or statement there.
Yeah. Basically, so we have. It's the same example that I will talk about here. I will skip this. I can go into this too. The case of fields.
Fields is essentially algebraic.
Yeah, but only if we use this, because we have two kinds of axioms defining fields. We have the first axiom, which says that every non-zero element is invertible. If an element is non-zero, then it is invertible, and an element or is zero or it's invertible. If we choose this axiom, then it's okay. The second one, but for the first one, we
need geometric.
Yeah, this is not, the first one is not geometric. We have to choose the second.
But the Morita equivalent, no? I mean, those two axioms say the same thing. I mean, they define the category of fields, no?
No, they don't. That's the point here. These axioms are classically equivalent, but they are not intuitionistically equivalent.
Oh, wow.
Yeah, this is something that Johnston proved in a paper. That actually, I forgot, there is a third axiom. There are three notions of fields, not only one, because for an arbitrary topos E, there are two different notions, at least, of fields internal to E. There is a notion internalizing this axiom and a notion internalizing the second axiom. But they do not agree. They agree in the case of set theoretic models, but they do not agree for every topos, because this
is this well known? This stuff?
What? Johnson's?
Yeah.
I think
Yeah,
that
they discuss it in McLean and Mordick's book.
Yeah.
Oh,
Like
they
different
discuss
fields, right? Sheaves and geo.
yeah, I think that the name of this paper is Fields and Spectra.
Okay.
It's
anyways.
yeah, it's an interesting, very interesting thing that we have three notions of fields, and that's something very suitable, and very subtle that can happens in the, because sometimes we have axioms that they are equivalent, but of course the set theoretic models are the same. But when we internalize the notions in topos, we have two notions differently. So, and from this we can see that first thing, that the external and the internal point of view are not equivalent, and more than that, sometimes a category which is N, which is a category of set theoretic models for some theory, that's the point. We could be tempted to define the internalization of N by interpreting T. So, but the problem is that there could be that there exist two different theories, T and T prime, for which with the same category of set theoretic models, but with non-equivalent categories of models for every topos. And so, when we internalize, we are actually not internalize the category, we internalize the theory, as the example of fields shows us. So today, internalization is more like an art than a science in mathematics. We don't have a theory of internalization concept. So, in some sense, part of this work that I'm engaged now is an attempt to at least define, try to make it more conceptual and more. So, in some sense, but I don't know if I have enough time. I don't know. Okay, so maybe I'm going to stop here.
Okay, so here's an idea. Just slowly go through the things, the slides till the end, so that if somebody's watching it, they can stop and listen.
So this part is still
Sketchy.
sketchy. So, but it's highly influenced by the works of Haller, in some sense, because so there is a point that I try to define what is a shift theory in general. Then some other definitions here.
You know, you're just going to have to come back and give another talk. That's it.
And I hope to have more material into there, because, but it's Here there is this point of geometric fragment, but basically the idea of of this internal homotopy theories is to replace localizers by couples of this kind, which is a theory T and a fragment of the theories of arrows of T, W, and try to generalize a result due to Silberback in the paper Schieffe-Fiebel homotopy. I guess that's Schieffe-Fiebel homotopy model theories. Schieffe-Fiebel homotopy model categories. I guess that's the correct name. So one of the goals is an attempt to generalize this theorem, and to also to understand this theorem in a more conceptual way. But here are some things some computations I already did, some things I already proved. So, okay, but then there is an idea of shift localizers, here some ways to construct internal homotopy theories. Here I follow the idea of sketches, but
I thought sketches work for essentially algebraic things.
Yeah, in general, there is a notion of a sketch.
Oh, this is a notion of a geometric sketch?
Yeah, a notion, here it's a notion of geometric sketch, which is the idea that, we have the category A, and then we take the exact completion of A, and then we take the topos of sheaves of this exact completion, which is the freely generated topos of A. Then geometric sketch will be just a couple given by a category A and a small set of morphisms here in this topos. Of course, that this generalizes when we have cones. We can view these cones here in this topos, and the idea of geometric sketch is it captures the idea of structures which are defined in terms of finite limits and arbitrary inductive limits. So that I was trying to define a notion here. I don't know, maybe people already know this, but this notion of geometrically accessible, if this is the category of models for some geometric sketch, and I strongly believe that these are the categories that are able to be internalized in some sense. I think, at least, of course, that we can internalize a sketch which is not geometrical, but the point is not only the internalization. I also need good functorial properties, and these good functorial properties, I think that they are only available for geometric sketches. That's the best we can ask. So, well, thanks.
There you go, one more. All right.
Thank you.
All right. Thank you. Like I said, that's part one of the talk. You can add. Any questions? Any unhappiness? Any discussion? Thank you. Really. Finally, somebody made sense out of it.
So, how do derivators come back?
Sorry?
How do there's like two parts of the talk, right? So like, what are derivators, and then like internal, trying to define what it means to have like a homotopy theory in a topos.
Yeah.
So let me just try and understand something first. So like, you have a topos, you can define a category in the topos, right?
Yeah, we can define a category from the topos, which is the category of modules for T.
No, I mean like a category internal to a topos.
Ah, yeah, you can. Yeah.
Are you trying to put a homotopical structure on that category internal to a topos, or are you trying to do something different?
No, I'm trying to do something. If what I'm trying to do, if I could really do what I'm trying to do, then this would be one case, one application, because we are just internalizing the notion of categories and defining homotopy, some kind of homotopy structure there, some kind of weak equivalences. So this, but I'm trying to do this for an arbitrary category and an arbitrary localizer. So at least an arbitrary category, at least a category that we can internalize in this sense. But as I said, that's not actually for the categories, for the theory that we internalize. So in the sense when we think about categories inside the topos, we internalize the theory of categories.
So you want to give a homotopical structure to any geometric theory in a topos?
Yeah, basically. Basically, that's the idea. And also for the class of arrows, because
But what does that even mean for the topos set?
The topos of set?
Like, so you have some theory, like groups, and you want to put a homotopical structure on that. So like, would that be the category of groups that you're putting the homotopy? I don't understand like what the homotopy structure is.
Okay. No, it means like I don't want to define a homotopy structure for every theory, geometric theory. I want actually to understand what is the homotopical notion of a geometric theory, in the sense that I have a theory and a theory for arrows, for the arrows of this theory.
So I'm talking about like homotopical monoids and homotopical groups. I think that's what you're talking about, isn't it?
Yeah, I think that in some sense, yes. If we have a notion of homotopy, so I don't know if I understand the question correctly, but that's...
Yeah, I guess I don't understand my own question.
No, but he wants you to make a clearer connection between the first part of your talk and the second part of the talk, and that's, in other words, you didn't use the word derivator in the second part of the talk. So somehow make an English sentence with the word derivator and the word internal homotopy.
Yeah, they're going to be connected some sense.
Okay.
Because the idea is to define a kind of. That's actually the project of. This is a part of the project of my PhD. I'm trying to generalize the notion of derivators to 2 points. Define what I call topological derivators, which are derivators which are not defined on small categories, but over topoi. There are strong evidences that they exist, because, and Grothendieck, in a letter to Thomasson, he speculates that, oh, I guess then actually there is a notion of derivator defined over topoi, and every derivator is actually a restriction from the derivator defined over topoi. When we take the small category, then we take it to the topos of pre-sheaves, and then we apply topological derivator.
So this topos derivator takes in a topos and gives a category for every topos?
Yeah.
Would it be something like if you have a theory, then you could send a topos to the category of models in that topos, and that would be a derivator and
yeah, a
topoi type of thing?
Yeah, precisely. That's our point. When we have a geometric theory, then this is already an example.
The same thing as
a geometric theory is a pre-derivator of localization already. When we have a geometric theory, we already have a pre-derivator over topoi. In some sense, it would be interesting to study more properties of theories in order to define derivators over topoi.
So can you take like a geometric theory? So you said, if I have a geometric theory, then I can get a geometric theory of its arrows. Is that right?
Yeah.
And then I can choose some of those arrows somehow and localize them and get another theory? Is that a thing you're saying?
Yeah, we can choose some arrows, but what does it mean to choose some arrows is to establish like fragments of the theory, some axioms that we impose that these arrows must satisfy. But what kind of, what would be the nature, like the logical nature of these axioms in order to everything happens well, like it happens.
Like, do you have an example? Like, that's what I wanted, like, can you take like the theory of groups, take some like, something about the arrows, localize and get something that I know?
In the case of groups, no, but the case of simplicial sets is an example, which is the homotopy theory of simplicial sets. So we can write we can write a geometric sentence in the theory of simplicial sets, which says precisely when a simplicial set is concomplex. So there is a way to do this, and Beck did this already for this case, but he only made for this case almost. So I would like to try to understand what would be the let's say the general nature of these kinds of axioms. So it's a kind of this is one of the parts of this internalization.
But so, all right, so you have a geometric theory of complexes. Is that?
Yeah.
And so then you localize at some arrows and then something happens? Like, I don't understand.
Complexes, yeah, we actually localize the simplicial sets, but in order to make everything good, we actually, that's the point. First we need to define a notion of locally vibrant objects. Thinking about the homotopy simplicial sets, okay? So if we have a topos, you take the simplicial objects in this topos. So we, in the model structure of the category of simplicial sets, vibrant objects are the complexes, and we have the notion of vibration. So we need to think about how to internalize the notion of vibration to a topos. We can do this using, there are many ways, but one of them, we take, we can define a notion of local right lift property, because we are in a topos, so we have to think locally. When a topos has many points, for instance, we can just say that for every point, when we take the fiber, this is a vibration. This is one of the ways, as we do for local rings. Then this is one part. So we define the local vibrant objects in the topos. But the problem is, and for this we can define the homotopy theory. But this is just we don't have a model category in this way. We just have a category of vibrant objects in the sense of realm. So in order to have the complete model category, we have to consider all the simplicial sets. But then, to define weak equivalences, we must first define the vibrant replacement, and then we define the weak equivalences using the vibrant replacement. Because, but it happens, fortunately, that the construction of the vibrant replacement, which is a categorical construction, for the category of simplicial sets is geometrically. It's a construction which only uses colimits and finite limits. So we can internalize this construction for the simplicial topos in this simplicial sets.
I think we should stop. But anyways, we'd love to hear the rest of it.
Oh, thank you.
And next semester, whatever you want, we'll do that.
Oh, thank you very much.
Anyways, thank you very much. It's a pleasure. Oh, and next week is Mike Schulman on setoids or something like that, another type of derivatives, the derivators.
Oh, nice.